Right, so now this is a completed drawing for, or completed points for safety. Rotating antenna, radio frequency, working at height, procedures for working on a ship and so on. Ship HAZ, so that's what we have ship HAZ for. Working at height we have PPE, radio frequency, we've got to be careful of microwaves, so the heating effect, that's that there. The EM spectrum, I've drawn it, so we've got the visible spectrum there that we can see, and I'll try and cross-hatch that one. Looking at the green, no, can't find it. Oh, there it is. So we have, that's the visible area. Okay, and either side of it we've got the infrared at the low end, ultraviolet at the high end, frequency that is, remember the axes. We've got infrared there, and then below it we have radar, and then below it further still we have radio. Above we've got X-rays, ionizing, not good, and in terms of energy, as frequency goes up, so does energy. In terms of energy, what we have to be careful of, and this is where I've got the derivation of the Einstein's equation that he, when he developed the I can't try and think of the experiment now. So his experiment was the photoelectric effect, that's it. So E equals HF. So if we replace F with C over lambda, we get E equals HC over lambda, and that's those two there are popular formula used within physics. Okay, so all I'm just trying to say here is, as frequency goes up, so does energy. Energy you have to be careful of, because obviously that's that is harmful to life. So finish that. Now I want to go on to oh yes, that there is the graph, and you've got this in your books, or your lab workbooks as such. So we've got frequency going up in terms of the axis there is megahertz, 10 megahertz, 10 megahertz, 100 megahertz, and then a gigahertz, 10 gigahertz rather even. Okay, so what we're trying to do is we're trying to show that depending upon the frequency will determine, basically in this area here, the safety aspect is much better, because the ionization, yes, so the ionization there is less effective at, say, if we had the frequency low, it's quite high, around about 10 to the 2, that's not so bad, but then as the frequency goes up, then it has greater effect, and that's what we're showing you there. There are various bodies around that have influence on this, or have looked at this. So you've got ANSI, IRPA, and there's another one of Canada. Okay, there is also an international body that dictates what your frequencies are in terms of safety. Okay, and this is the ICRP, that also covers non-ionization radiation as well as ionization radiation. Okay, so the ICRP, that's the international governing body for that one. But you have to be careful when you plot your energies where your radar has effect on the body. All right, so that's that. So let me continue. Let's just check that we're still recording. Yeah. Right, now I want to clean the board. And so we've discussed safety. Dry it off. Right, now the next thing I want to look at in terms of your notes, yes, right. What we want to do is we want to compare the energy of a CW radar, so continuous wave radar, and then we have pulsed radar from the duplexer, and that's the device that allows the antenna to work as to perform two jobs: transmit and also receive. What we have is a continuous wave radar. Will be simply in terms of time, so that's amplitude, time. Okay, it'll just continue oscillating all the time. Pulsed, however, that's different. We send out a burst of energy. So, and the difference is that we're transmitting all the time in terms of continuous radar. That's where your continuous comes in. We send out a pulse or burst of energy from a pulse radar. So the radar that we looked at earlier on with the modulator and the oscillator and the high level mode was a pulse radar. So within your document you should find something discussing yes, there you go. So it's question 1. Use the preceding information to calculate the power density of the aperture of the horn. So, for a continuous radar, you use the equation power density, P dot D, power density, equals P average over area. So P av over area. When we say the area, we're looking at maybe a feed horn. So at the front of your antenna, you'll have something looking like that. Okay, and then you'd have the antenna here, like so, and this would be radiating energy. So there's a little wire that goes around like that. So we're looking at the area of the horn there, and that is 25 centimeters squared. Okay, so the question states something like, it goes through and it says 25 centimeters is the antenna, and it's 2 milliwatts. So all we do is we plug in there 2 milliwatts over the area, 25 cm squared, and then that calculated, we end up with just bear with 720 milliwatts per square centimetre. So milliwatts per cm squared, like that. So that's that example there. Agreed? So that should be the answer that you would find for question 1. Okay. With pulse radar, what we end up with is we have to use our pulse average, or our pulse density, power density rather, P average, power peak, dot, I'm going to use dot rather than the multiplier, okay, against tau over T. Now you're wondering what tau is with respect to T. When we send out our next burst, okay, what we do is we look at the time there, which is called the PRF, and we look at the time here, which is called tau. There's tau, PRF is also T. So we're looking at the ratio of off to on. Okay. So looking at off to on, what we have is we have the derivation of Pav equals P peak dot tau dot 1 over T. So I've taken the T out, okay? Now 1 over T is equal to PRF. There. So we can substitute that 1 over T for PRF. So Pav equals P peak dot tau dot PRF. That's the equation that we need to use. So in terms of a pulse radar, as opposed to a continuous wave radar, regarding the power density for continuous wave, we just do simply that. However, if we've got pulse radar, we've got to do that equation, then we can do that equation. Okay, so that's step 1. And then step 2 is PAV, so PD equals PAV over area. So that's our second equation. And in short, what you'll end up with, in terms of continuous radar, will have more energy emitted when CW is compared with pulsed. So, and the reason is we work that out and we work that out. So those are your equations that you need to work out regarding, so yes, so let me find it in your workbook. So those are questions 2 and 3. So questions 2 and 3 in lab workbook. That's how you answer that. Any questions? I hope not. Right. Let me have a look at what's next now. So those are my notes, and I need to have a look. So we've discussed that. Right, so now what you're going to be doing is you're going to be going on to the LabVault trainer equipment. Just briefly looking through. So question 1, we've done that. Question 2, we've done that. Question 3. Yes, question 4. Use the preceding information to calculate the maximum average power density of the parabolic reflector. Okay, so I'll just add that one. Okay, so we've looked at the horn this time, so that's called the feed horn. And I've drawn the parabolic reflector there. So the feed horn, the area is 25 centimetres squared. Right, so let me just wipe the board, and I'm going to amplify that, or I'm going to elaborate on that one. So, what we're interested in is okay, I'm going to draw the antenna now. So something like that. I'll try, and then mounted on it is a metal boom. And mounted on that metal boom is the okay, now what we're doing is we're comparing. We had 2 milliwatts and the area was 25 centimetres squared here, and that was the edge, that was the area of the feed horn. The reflector that is 490 centimetres squared. So you need to compare the energy there with this energy here. So you have an equation for that already. I'm not going to give you that. and that is question number 4. So that's that, and then you have to comment on your results regarding the safety limit. So with that in mind, we've worked out the energy here, we've worked out the energy there, okay, and then you will see that's an important line, okay, and you will see that in terms of as you get further away, the energy drops. So here the energy is quite high and it should be quite low there. You should be able to calculate that. Alright, so then the next thing we do, and what I'll do is I'll assist you with this over the telephone, or if we can do a video conference call, that would be even better. But that depends on the Wi-Fi signal at Collingwood. So we're going to look at LabVault's piece of equipment, okay? So that there is a representation of all the boxes that you will see to the right of the PC, okay? So these are generally the boxes where you'll be playing around with, okay? So the radar transmitter and the radar synchronizer. You won't be changing any of the BNC connectors. Down here is the radar training module, and this is the part that communicates with the PC, and this is the part that sometimes goes wrong. There are 3 green LEDs, one above each of these modules here, and if they're on, that's a good sign. If they're off, or one of them's off, that's not a good sign. We won't be able to have the PCs configuring the so anything on the graphical user interface that you see on the PC for changing controls of the radar, they will have no effect on the RT, well, they're on the radar, on the LabVault system here. Okay, so that's a little bit on in terms of fault finding, because it does go wrong, and I'll have to for today, I'll have to try and work out how I'm going to explain that away. All right. Okay, so I'll see you in the lab now for the practical aspect of it, and that will be over the telephone or perhaps video conference, things all being well. Thank you then.